Are we recording? I think we're recording. Okay. Hello, everyone. So you're either seeing this Tuesday afternoon, but I doubt that considering it's almost 2 o'clock here. You're probably going to see it on Wednesday. One
Excuse the
sec.
interruption. Could Mrs. Smith doing Mr. McDougall's class?
Sorry about that. Okay. So we introduced, the different concepts, but and the idea of galaxies. So let me just go have a look back, and I gotta log in here. 1 minute. And da da da. Yeah, we talked about the the formation of galaxies, and yeah, the universe formation and how galaxies formed from dark matter and whatnot. We talked about that. Resume slideshow. So now we're going to get into a little more detail about the structure of galaxies. Now there are, first of all, many different types of galaxy shapes, and we'll get into that later this week. Okay, but right now we're mainly going to focus on the spiral galaxy. Typically what you're seeing there, nope, there, there, there. Okay. So that spiral, that's actually called a spiral bar galaxy. I don't know if you can see my mouse. You should be able to. In the center, there is a bar of stars. Right? And then we've got these spiral arms of blue and white gases and blue and white stars. And we can see this beautiful spiral pattern. Okay, let's move this. Okay, so that's what we're going to talk about. Now, one thing, right? You're looking flat on at that picture, but it's also flat. Okay, so we're going to talk about its structure this way and this way. And we're going to talk about how those spirals form. There's going to be a few YouTube videos posted as well where some astronomers, talk about the structure, and they're going to require a lot of thought, but they're actually quite good. So, next slide. And let's move me out of the way here. So this image you saw in the last PowerPoint, okay? And that was our view from Earth, right? What we could see of the universe, and that galaxies were clustered into these filaments. Okay? So let's read along here. Remember that galaxies are arranged into clusters and superclusters caused by quantum fluctuations in matter and dark matter that led to gravitational instabilities and then the formation of that overall filamentous structure. So matter is not evenly distributed. We've got these voids, and each one of these specks is a galaxy. And the galaxies, they cluster into local groups, local clusters, and then excuse me, superclusters. So we had our galaxy. Sorry, I'm going to pause it and get a drink of water. 1 second, please. Sorry about that. Where was I talking? Yeah, so we have our galaxy, and then from our galaxy, we have the local group, right? So we've got the Milky Way, the large and small Magellanic clouds, then we have Andromeda, and then we belong to, the Virgo cluster, and then from there we have that big cluster, it's that Hawaiian name, I can never say it, Laniakea. Anyways, that huge supercluster, and then that belongs to larger and larger things, creating this. Remember these black triangles? We can't see what's there because we're within our galaxy, and our galaxy is blocking the view there. So, what is a galaxy? Let's move me over here. I guess I'll just hang out in the corner here. La, la, la. Okay, galaxy, a massive collection of stellar, so meaning stars, and interstellar matter. So, interstellar matter, gas and dust and whatnot. So, a galaxy is a massive collection of stellar and interstellar matter, stars, gas, dust, neutron stars, and black holes. And we'll talk about those. Those are all, or were, stars at one point, right? And they're isolated in space and held by their own gravity. Right? And we are aware, right, just looking out in deep space, that we saw that Hubble Deep Field image, right, where they looked at a single point in the night sky, and they just zoomed in on it, and they let the telescope view for days and days, gathering all the light it could. And we know that there are billions and billions of galaxies out there besides our own. And we can't see our own galaxy. We are within it, but the evidence suggests that we live in a spiral galaxy. So the rest of the slide here is all definitions, but let's look at some images first, and I'll come back. Okay. So here, right, I'm pretty sure this is Andromeda. Right? And if we look at this galaxy, we have the galactic disk, the galactic bulge in the center, and then surrounding 360 degrees is the galactic halo. This here is a smaller galaxy that's being attracted to the larger galaxy. So you got the bulge in the center, right? And in that center, there's in almost all galaxies, there's a supermassive black hole that is the source of gravity holding everything together. Right? You've got the galactic disk made up of gas and dust and stars. And then we've got the halo forming around them. Now, we haven't gotten into star formation yet, but as we talk about stars, generally large, new, hot stars burn blue. Okay. And older stars or cooler stars are generally a reddy yellow color. Our sun isn't particularly old, but it's kind of a yellow color because it's small and it's cool. But the youngest stars are the biggest stars, and they burn the hottest, which is generally a blue color. Okay. So if you look at this image, you may be asking, well, what is this little wave thing here? Right? And this is showing what spectrum, what part of the electromagnetic spectrum they're viewing this image with. And it's in red here, so it's viewing with visible light. Right? Visibly, this is what we would see of this galaxy. Now, if you're looking into that the Andromeda galaxy through a telescope, you won't see that. Okay, all you'll see would be a vague impression of that. To get an image like that, you need to have a telescope focused on that galaxy for several hours, gathering light and storing it in a computer. And then a computer compiles all the light together. Unfortunately, you will never see that in a telescope. You would see a fuzzy smudge, and you'd have hints of these lines. Okay? So, moving forward here, this is a picture of a spiral galaxy. Instead of this way, it's turned on its side. We have, and this is kind of like a diagram of what we think the Milky Way would look like. You've got the galactic disk, okay, and this galaxy being 100,000 light years wide. Light traveling from here would take 100,000 years to make it to the other side. Okay, we've got the galactic bulge in the center, okay, and then the halo is a group of stars orbiting 360 degrees around in a sphere around the galaxy. Okay? These stars are trapped by the gravity of the galaxy, but they're not, part of the arms. Right? Stars in the arms are spinning around and around the central core in a flat plane. Stars in the halo are zooming around 360 degrees, like my mouse is doing, is all around there. They're not trapped in the flat plane, but zooming and zooming and zooming and zooming. Yay, zooming. Okay, so the structure of a spiral galaxy. We got the galactic disk, right? Immense, circular, flattened disk made up of luminous stars and interstellar matter. Okay, so stars and gas and dust. In the galactic disk, there is a lot of star formation happening. Right? Those blue areas, they generally correspond to new stars, star formation. So you've got regions of active star formation, and you've got old stars there as well. In the bulge at the center, lots of gas and lots of stars around the center of the galaxy, right, containing lots of old and young stars, right? But if we generally look at the overall color, it's more yellow. So there's still star formation happening there, but you're going to find more older stars. Lots of star formations happening there, but you're going to find a lot of old stars too, giving it its more yellow tinge. Right? In the center, the point about which the galaxy rotates, and it's thought to be a supermassive black hole. Let's move on up. I'm in the way. The halo and the halo stars, they extend above and below the disk, okay? And they contain clusters of old stars, very little gas, very little dust. If you want to make new stars, you need hydrogen gas. You need clouds of gas available that are going to collapse under their own gravity. And then, as they collapse, gravity squeezes the hydrogen together, and then you get nuclear fusion. The hydrogen fuses into helium, and that nuclear fusion releases tremendous amounts of radiation, heat, and light. In the galactic halo, there's very little gas. So in the galactic halo, you only have old stars. Okay? If we look at the note there, let's zoom on down. Where's my mouse? There it is. All stars in the halo are over 10 billion years old. Right? Very, very old stars. The universe is 14 billion years old, and these have been around for 10 of those 14 billion. And then we got the globular clusters, spherical collections of hundreds of thousands of stars tightly bound together by gravity that orbit. So they're almost like a small galaxy in their own that orbit around the bigger galaxy, the stronger source of gravity. Okay, so galaxy, spiral, bulge, disk, halo orbiting around, right? In these smaller clusters, right? Smaller galaxies, sometimes they're called clouds or a globular cluster. Okay, let's move to here. I'm not in anyone's way here. I'll just chill out by this diagram. Okay, the entire disk is spinning around the galactic center. So when we think about galaxy formation, you've got a large cloud of gas that gets pulled in by gravity, right? And this cloud of gas is massive, right? It starts forming stars and whatnot. And as it gets tighter and tighter, it slowly starts to spin. And think about, and this applies to the formation of the solar system and, tornadoes and hurricanes, right? Think about a figure skater. And as the figure skater, right, if they want to start to spin, they pull their arms in and they start spinning faster and faster. The same thing happens with the galaxies or stars or solar systems or tornadoes, right? As they slowly start to spin and the material gets pulled inwards, they start to spin faster and faster. So as this gas cloud starts to spin faster and faster and faster, that spinning causes the glass cloud to flatten out. So you get this rapidly spinning disk. Think about if you've ever seen videos or been to a pizzeria where you've got that person and they toss up the pizza dough and they're spinning it and then it flattens out. Same idea. So the rotation period of an object in the galaxy depends on the distance away from the center. The closer you are to the center, the shorter your rotational period, how long it takes you to go around. Okay. The sun is 8 kiloparsecs away from the galactic center, meaning 26,400 light years away. And it would take our sun 225 million years to actually rotate once around the galactic center, or one galactic year, right? 225 million years. Okay, next point. Globular clusters and individual stars in the halo and stars in the bulge do not share the same rotation pattern, I should say pattern, of the disk. Okay? Stars in the disk are revolving in a flat plane around the galactic center. Stars in the halo and the bulge are zipping around like a bunch of bees in a hive swarming around a hive, right? It's all 360 degrees. I look like a fool, right? Just right all the way around. If you're in the disk, you're going around, let me get right centered here, you're going around the disk. The bulge, bees, the halo, bees, but longer paths. So stars in the disk follow circular orbits. Halo stars, right, their path takes them high above the galactic plane and then far below the galactic plane. Stars in the bulge orbit randomly around the galaxy center while tending to stay within that bulge. The gravity's strong enough to keep them there. So we've got three distinct areas of star movement. The disk, spinning flat around. Okay, the halo stars spinning all sorts of ways, high above and far below the galactic plane or the disk. Right? And then you've got the bulge, right, close to that central black hole where the stars are zipping around, and they usually stay within that galactic bulge. Let's see if I can stay centered here, right, zipping around in the center. Now, this part is a little confusing. Why are there spiral arms? Okay, so I want you to think about something first, right? Think about, you have a cup of coffee, right? And if you have a chance, actually try it, right? Get a cup of coffee. If you drink coffee, you pour the cream in and start slowly stirring it. So you got your cup, pour the cream in, slowly stir it, and you'll see the cream form a spiral. But over time, that cream gets spread out equally everywhere, and you lose the spiral. This is what would happen to a galaxy over a few 100 million years. But our galaxies are billions and billions of years old. But there still is a spiral pattern, right? The spinning itself should have totally disrupted that spiral pattern. Right? If we look at this diagram, right, this is what should happen. Right? You've got some spiral arms due to spinning. 1 second.
Can I have your attention at the bell? All baseball.
So you've got this slow spinning, right? And as it spins, right, those arms of the stars, they get stretched out as it's spinning, right? And as it spins, just like the cream, they would get stretched out even further and further. And eventually you would disrupt the spiral completely. So just like the cream, there's no spiral. The cream is spread out evenly, right? In this case, the stars had spread out evenly to have just this flat disk of stars without the distinct bands we see in, this galaxy or in this image of what we think the Milky Way is with distinct bands. So where do those spiral arms form? And that is the question. So let's read this slide together. According to differential galactic rotation, right, objects closer to the center rotate faster. So this is standard for any spinning system, right? Even if you think of our solar system, Mercury is moving much faster than Jupiter and Saturn, right? Its speed because it's closer to the force of gravity, its speed is much quicker. Right? The further out you go from the center of a spinning system, the slower your speed. So objects closer to the center rotate faster. If the spiral arms seen in the Milky Way were the only material of the galactic disk, so if they were the only thing there, then the uneven rotation, stars in the center of the arm part of the arm closer to the center compared to the part of the arm far away. So if we were to look here, the arm close versus the arm far away, the stars in the center would be spinning around much quicker and quicker and quicker, and these ones would be spinning around slower and slower. And it's called wind up, right? The uneven rotation would cause the spiral arms to stretch and wind up around the center and eventually disappear over a few 100 million years. These galaxies that we look out in the night sky and see, these spiral ones, right, they are, excuse me, they are billions of years old. Right? If the spiral arms were made of just stars, and that's the thing that formed them, there would be no spiral galaxies left. Just like a cup of cream, as you stir it, right, that cup of cream, this cream gets spread out evenly. So the spiral arms would not have been around long enough for astronomers today to be able to observe them. Therefore, the spiral arms are probably not the only stuff that comprises the disk. And there are some pretty good theories as to why this is the case. Right? Watch the YouTube video. I'm gonna the one that is the best. I'm gonna put right after my little introduction that I'm going to do. Okay, that's the end of the day here at Northampton. Okay, but the best one's about 12 minutes long. It's some of it's a bit challenging, but if you do some heavy thinking, you'll be okay. If you're unsure, please come talk to me or send me a message. So the idea is that we have spiral density waves. Okay? This theory explains the spiral arm. The arms themselves are not the only stars in the system. Okay? They are not the only stars in the system. They are areas where stars are clumped. Right? And because the stars have clumped, right, it's brighter there. There's more stars there. And because there's clumping and gas clumping, you get more stars being made there. Right? And it's going to be hard to explain. The videos will help a great deal. Okay. The idea is that the galactic disk is full of stars, gas, and dust. We have waves of increased density that move through the disk, compressing gas and dust, creating areas of new star formation and activity, creating luminous spiral arms. As the density wave leaves this bright arm, that area dims and the newly compressed area experiences increased star formation and glows brightly. Hence, the spiral arms are not spinning around like cream, right? But these are waves of density traveling through the disk, compressing stars, compressing gas, right? Creating bright areas. But these density waves are traveling through the disk. So these waves of density are compressing the disk, and these waves move through the disk, creating areas of increased star formation that look like spiral arms. But these spiral arms aren't actually spiraling around the center part, right? They are waves of dust moving around. And let's see if this will actually work. Okay, I don't know why this one didn't hyperlink, but let's go to this. Control click. Not working. Control click. Not working. Okay, I'll post these. They'll help explain the idea of the spiral density waves to help understand the spiral arms. Okay, But remember, to get stars to form, you need compression, you need gas being compressed. So if these spiral density waves, when I talk about density, we're talking about areas of lots of stars versus stars being spaced out. If you get areas of stars tightly together and gas tightly together, one, that area is going to look brighter because there's lots of stars there. But if you've got areas of gas being compressed, right, you're going to get new stars being made. New stars burn really hot, really bright, very luminous, creating these blue spiral arms. Okay, the video will help you understand what's going on. I really wish we were in front of a class together and I could talk about this with you, right? Oh, here we go. Let me see. I don't know if I can bring this over because that's there. Let me figure it out. You just bear with me here. If I pull this over here, looks like it's working. So this is just an animation, right, to kind of express the idea, and I really hope you guys can see this. Right? Excuse me. This is just a simulation to talk about density waves. These spiral arms are areas of high density, and in between them are areas of low density. Stars can actually move between these areas. A star that is in here isn't always going to be part of that arm. It can move out and across and around the galaxy as it orbits. So as stars orbit around, right, they may enter a spiral arm and they may leave a spiral arm. So let's just hit play here. Make it bigger. Okay. So what's hard to notice is if you look at the stars aren't staying in the arm. This is the arm, this is the arm. Stars are moving in and moving out of the area of high density. Okay, that area of density, those aren't stars permanently attached to there. You just got a cluster of stars, so it's brighter. Another analogy is a traffic jam. Think of a traffic jam on the 401, right, heading into Toronto, right? You've got a traffic jam, right? But that traffic jam, those cars don't stay there. The cars at the front can leave the traffic jam and start moving. Cars behind come up and get caught in the traffic jam. So you're always having cars leaving the jam and then cars moving into the jam and leaving and moving and moving. So you got this area where there's a high density of cars, the traffic jam, and cars are leaving and cars are coming in. So you've got this cluster, this dense spot where cars are leaving, cars are coming in. In a spiral arm, stars are leaving, stars are coming in. But in that spiral arm where there's a high density of stars, you've got increased brightness because there's more stars in the area, more light. And if you get gases being compressed there, you're going to have the stellar ignition, the formation of new stars. Let's try this video here. Let's bring this over. Rachel. Let's move me up here. Okay, let's close this. This is something that you're going to have to think about, right, and process. I don't know why this link isn't opening. I'm going to post it. Watch it. It's, like I said, it's 12 minutes long. It is good. So now it's like, okay, well, if those spiral arms aren't caused by the spinning motion, but by density waves, where do these density waves come from? And there's theories, right? We've got theories we don't know. Right? So it might be due to the gravity of large objects nearby, like other galaxies, like the Magellanic Clouds, right? Right? There's the large one, there's the small one. Right? This is a spiral arm of our galaxy, and there's a large Magellanic Cloud, there's a small Magellanic Cloud. Okay, so maybe their gravity is causing the density waves. The astronomers have noticed a trend that spiral arms seem to be more consistently around galaxies that have other galaxies nearby. So maybe it's the gravity that's doing that. The gravity of these objects pulling on our galaxy.
Mr. Sotos, please contact the office. Mr. Sotos.
Okay, maybe it's caused by instabilities in gas near the spiral bulge. So in that galactic bulge, so there's some kind of instability that's traveling outwards. Okay? Or and let's go back to the picture of our galaxy. Right, there's a bar in the center. Some galaxies aren't a bar, some they're just a spot, a circular globe. But in our galaxy, instead of being a perfect circle, it's elongated out. So maybe the spinning of this elongated object somehow contributes to density waves. We don't know. Okay? So, I've left some questions that I want you to answer. I will make these into am I going to make these into an assignment? I'm going to think about that because I do have an assignment I want you to do. Actually, no, these aren't going to be an assignment. This is homework. This is not an assignment. I do want you to go through and do them. Okay, so what I want you to do right now is to hit pause. Okay, answer these questions. You answer these questions, and then I'm going to talk about them. Okay, and I would copy this table down and answer this. Okay, so let me hit pause. While it's paused, I'm going to get a drink of water. Right, you take however long you need to answer these questions. Okay, so you've had depending on how long you took, right? I just hit pause. Why do we see the Milky Way as a band of light across the night sky? So let's go back and look. Where I went too far. Why do we see this? Because we're inside the Milky Way. We're inside one of the spiral arms and we're looking out and we're seeing another spiral arm of the Milky Way galaxy. That's why we see this. Okay, identify and describe the main parts of the galaxy. Right? The galactic disk, right? It's flat. Right? The halo, it's a large sphere around the galaxy, and the bulge, generally, a lot of people consider it to be like an oblong football shape. So, American football or a rugby ball shape. Star types in the galactic disk, right? You generally find, you're going to find older and newer stars, but you're going to see a lot of star formation. In the halo, it's all old stars, right? So you're going to see red and yellow stars. In the bulge, there's a lot of old stars, red and yellow, but there is a lot of star formation happening there too. A presence of gas and dust, yes in the galactic disk, no in the halo, yes in the bulge. Star formation, yes in the disk, no in the halo, yes in the bulge. Let's move me up here. Orbit of the stars in the galactic disk, they are spinning in a flat plane around the center. Okay? The halo buzzing around like a swarm of bees, right? Above and below, going around the whole disk, right? And the bulge, they're tight in the center, spinning around like a bunch of bees. Star coloration, galactic disk, we see a lot of blue stars. Okay, they're not the only ones there, but you generally see that blue coloration. Right? Blue coloration generally indicates hot, young stars. In the halo, right, generally red and yellow, so old, cooler stars. In the bulge, you mostly see a yellow color because there's old stars there, but there is a lot of new stars there as well. Moving on. Why are there no young halo stars? So why are there no blue stars in the halo? Because there is no gas and dust to make new stars. New stars, when they ignite, generally, especially if they're of a significant size, are blue and hot. Right? There is no fuel for new stars in the halo. Number 4, why can't spiral arms be clouds of gas and young stars orbiting the galactic center? If each spiral arm was just a stream of gas and young stars then spinning around the galactic center, just like the cup of the creamer inside the cup of coffee, that spiral arm would get stretched because the inside spinning faster than the outside, so it'll wind up and it'll just get stretched and stretched into oblivion, and we'd lose the pattern. So the only way we have spiral arms is the density waves traveling through. Okay, if anything of this confused you, please reach out to me and we can discuss.